Herkese merhaba. Bir sonraki konuşmacımız Ege Onur, Boğaziçi Üniversitesi'nde matematik ve bilgisayar okuyor. Şimdi konuşmasını yapmak üzere sözü Ege'ye bırakıyoruz. Buyur Ege.
First, thank you for listening me. I'm Ege Onur. I'm a senior undergraduate in Boğaziçi University, majoring in computer science and double majoring in mathematics. And today I'm going to talk about Monte Carlo statistical methods. Before beginning, I think it's interesting that it's called Monte Carlo methods. It's because randomity and chances are central to this technique, but this time we are not losing. So before beginning, I will give a brief motivation and then talk about random variable generation, then proceed with Monte Carlo integration, which is now widely used in all sorts of integration algorithms. And if time permits, I will continue to Markov Chain Monte Carlo and explain briefly the Metropolis-Hastings algorithm. So what is our aim? Actually, our aim is to solve various problems in optimization, random variable generation, or in statistical inference. And these problems may be deterministic inherently, but we still use randomity and simulations to tackle these problems. So what is our approach? As I said, we are using random sampling and repeated simulations in a certain way. So our concern is to show the convergence rates and also the expected errors while we are making these simulations. So why do we need these simulation methods, and what is challenging in statistical inference? Well, in statistical modeling, there are many difficulties, both at model setup and also at the inference time. So I'm going to introduce three models. The first one is mixture models. The second one is censored data models. And the third one is a moving average model, which is widely used to model time series data. And censored data models are also pretty apparent in modern data science. For example, if you're examining the lifespan of cancer patients, you have a limited observance time, for example, 10 or 20 years. And even if they live longer than 20 years, you can't observe it. So you censor some part of data. And I detail the mixture models and what's challenging in examining these models. First, the definition, it says that based on the observation that xi are generated from one of k elementary distributions fi with probability pi, resulting overall density x sampled from the sum of this k elementary distributions with probabilities pi. So far so good, but when you have a sample, you may have 30, 40, or generate n random variables, and it yields the sample density of the product of these sums. And you can see easily that it has k to the n elementary terms. And working with k to the n elementary terms numerically and also with computers is infeasible, not probable if you have large samples, because it grows exponentially, and exponential is pretty bad for computers. You can basically solve it. And also the standard moments expected value or variance, they're easy to compute nonetheless, but for example, likelihood, which is now widely used for all sorts of parameter estimation, you can't estimate it in analytical manner or even with standard numerical techniques. So we need simulation and we need Monte Carlo methods. As I said, we need this method. And the second part is that how can we simulate from a random distribution for any distribution? The thing is that computers are in general not random machines. They are deterministic machines. So we need to simulate randomness in a computer as well. And there are these sort of algorithms called pseudo-random number generators. And some of them pretty works well. And the most widely used is the KISS generator. The code of is pretty simple, but because it's not relevant, I put it there. And I think it's pretty interesting. You can read it. So luckily, with this KISS generator, we can generate any random number uniformly between the range of 0, 1. And well, if we have this like random variable, uniform random variable, the next question is that can we simulate any sort of random variable, or at least almost any sort of random variable? And the answer is yes. And here is the idea. Well, we want to represent the generic probability triple as the transformation of this uniform random variable. And like it means that we can get a generic random variable x as a transformation from the range of 0, 1 to omega. And this transformation is possible by the generalized inverse. Well, like the definition is pretty simple. You have an f, which is an increasing function on R, and the generalized inverse is the infimum of this quantity. So why do you need that? Because we are the cumulative density functions with probabilities, and they're increasing functions, but they're not always monotonely increasing. So that's why you may not have the inverse of this function, but you always have the generalized inverse. So working with the generalized inverse is handy. And here's a theorem that like makes it possible to simulate from any any distribution, any probability distribution. And it says that the random variable f generalized inverse u has a distribution f, provided that u is sampled from the uniform distribution in the range of 0, 1. And the proof is like pretty simple, but a little tricky. We just like take u and x arbitrarily from these quantities, these sets, and from the definition, you see that the f of f generalized inverse u is greater than or equal to u, and f generalized inverse f of x is less than or equal to x. And if you apply f to both sides, you see that the set on the left-hand side is equal to the set on the right-hand side. So like this also implies that the probability f minus f of u less than or equal to x is equal to the probability of u less than or equal to f of x. And because like u is sampled from the uniform density, and also like f of x is between 0 and 1, because it's the like CDF, we can say that it's equal to f of x. I think like the trick is there, because we sampled u from the uniform density in the range of 0, 1. So here is a little example that we will sample an random variable from exponential distribution. So like, as I said, let's do it step by step. We are using the standard exponential distribution, e to the minus x. And the CDF of f has the form of 1 minus e to the minus x, which is a simple integration. And this implies that the generalized inverse is minus log 1 minus u. And here in this Colab notebook, actually, we can sample random variables with this generalized inverse function. So it needs explanation. These are the required libraries. And here I'm defining the generalized inverse function as an inline lambda function. And like we now generate uniform random variables. For demonstration purposes, I generated 1 million random variables. And here is the plotting of these random variables. And then I just transform them with this generalized inverse. And like you see this apparent decaying behavior of this function. And like just to check, I sampled from NumPy's inbuilt exponential function, again 1 million variables, and the same behavior is apparent there. So like I proved, and I did it for your interest, and like we can proceed. It's another method. Proceed to the slides. Yes. So far, so good. Like theoretically, we can sample from any distribution that we wanted, but in practice, it's not always the case. Why? Because like we may have very complicated probability density functions. Not all density functions are like elegant as exponential density function. And moreover, even if you have an explicit form of your PDF, you may not have the explicit form of CDF. And even if you have the explicit form of CDF, inverting the CDF may be infeasible or may lead to computational infeasibilities. Like especially if you are if you have like univariate or if you are like multivariate probability density functions, then like inverting matrices leads to numerical instabilities. So actually, that's why we need another method. And the proposed method is accept reject methods. Actually, they are like a class of methods, but I will give the simplest one and the most easy to understand one. So like, here's the proposal. If we can find an auxiliary density G and a constant M such that f of x is less than or equal to m times g of x on the support of f, then the accept reject algorithm can be used to generate random variable y distributed with respect to f. So here's the algorithm. It's pretty simple. We are just like generating generating x from the probability distribution G, and u from the probability uniform probability distribution. And in the second step, if u is less than or equal to f of x divided by m times g of x, we accept y as x. Else, we return to step 1 and perform the same operation again. It's a recursive definition. And here is the proof of algorithm. Like, if you have y, the algorithm already accepted x. So that's why actually py less than or equal to y is equal to px less than or equal to y, given that u less than or equal to f of x divided by m times g of x. And like, just use the bias formula and write the formula in terms of the joint distribution divided by pu less than or equal to f of x m times g of x, and like just expanding it into iterated integrals, you will get the result. So again, here is an example of accept reject algorithm. Now we will simulate the scaled exponential distribution. Like, we sample u from uniform distribution and take g as uniform distribution and m as 1/2. And because we took m as 1/2 and f of x is already less than or equal to 1/2, like the criteria is satisfied. And so the accept reject method is applicable and the sample code is there. So now we have this accept reject method. And like, we sampled these variables as I suggested. And like, we sample random variables with this accept reject method as follows. And I just plot them. And like, using numpy's again inbuilt function, we sample with numpy as well. And like, the same behavior applies. So like, we can sample at least from most of the distributions with these methods. Now, how can we use them? The first case is in Monte Carlo integration, but like, we have other numerical solutions like Riemann sums, etc., etc. Why don't we use them? Because sometimes if you have like more than 3 or 4 dimensional functions, using Riemann sums is infeasible, in general infeasible. So you may need some sort of efficient algorithm to calculate these integrals. Well, like, the theory of Monte Carlo integration depends on the law of large numbers. The first one, the weak law of large numbers, most of you maybe already know. It states that the sample mean converts in probability towards the expected value as like the sample size increases to infinity. And like, here, one thing that's important is the convergence in probability, and it's defined there. And the second, and actually the most important definition for this theory, is the strong law of large numbers. And it says that the sample mean converts almost surely to the expected value. And almost convergence is given in this definition. So like, start by the first step. We know that the expected value of h of x is this quantity given by this integral. And by strong law of large numbers, we know that h bar of m converges to this expected value. So actually, like, we can use this, like this definition to calculate this expected value. Not calculate, but approximate this expected value. And the thing is that, for example, just think simple. For example, if you're integrating some sort of function between like 0 to m, you may take the density function as the uniform density function and sample random variables in this range, and then like just divide by the number of random variables that you have generated. So it's simple as that. But like one thing that's important is that how many samples you need to have a good approximation. And like luckily we can find that. It's because like h square, if h square has a finite expectation under f, the speed of convergence of h bar of m can be determined, because like the sample variance is given by this quantity, and it converts almost surely to the variable h bar of m. So like then by the central limit theorem, this quantity, this total random variable is approximately distributed as the standard random variable. And it enables us to assess the speed of convergence and also the error. And I think it's like really beautiful, this quantity there. Like I'm amazed by it, how simple it is and also how useful it is. And the thing is that you see here that there is no dimension. Even if you have like 30-dimensional function or like 40-dimensional function, you have no relation with dimensions. So actually, like with high-dimensional functions, it's like one of the few methods to use. So it's like the simple example of Monte Carlo integration. Most of you already know that. You can find the pi number using this Monte Carlo integration. You just like sample these numbers, and you like take the ones that are inside the circle and divide it by the total number of random numbers. And I'm not going to open the code because I think it's easy. You can skip it. Oh, do I have time? Okay, thank you. So I'm going to be quick in Markov chains. Well, they're pretty useful as well, because we have this method called as Markov Chain Monte Carlo, and even if like we can't distribute from probability distributions with accept reject method or like transformations, we can use Markov chains. And nowadays Bayesian inference is widely used, and they lead to really complicated statistical setups. So that's why people generally use Markov chains nowadays to tackle these problems. So first, the definition. Intuitively, it's a sequence of random variables that can be thought of as evolving over time, with probability of a translation depending on a particular set in which the chain is. Well, like because of like this intuitive definition, we need a transition kernel because we are changing the states all the time. So here is the definition of a transition kernel. It's a function k defined on this set, such that for all x in x, kx dot is a probability measure, and for all a in like the world in this space, ka is measurable world space. And with this definition of transition kernel, we can define the Markov chains. And given k, a sequence of random variables is a Markov chain. If for any k, actually, like the probability of the random variable in A, given that all these previous states, is equal to the like the probability of only the last space, only the last state. So it says that actually you have no memory in your model, and it's called homogeneity or memorylessness. It's also like explained yesterday. But like the study of Markov chains in like continuous distributions is really complicated, and like we need lots of phenomena like reducibility, ergodicity, etc., etc. That's why we are using the discrete case. And also like discrete case is more useful because computers work discretely. So like I defined this fundamental theorem of Markov chains with discrete distributions. Let X be a finite set and the kernel a Markov chain indexed by X. And if there is null zero such that, and null zero such that k to the n xy greater than 0 for all n greater than null zero and 0, then k has a unique stationary distribution pi as n goes to infinity. So it says that like at which point you start, at which state you start, if you have this property, then your Markov chain, iterated Markov chain converges. So it's pretty useful. You always know that you have a stationary distribution and you will converge it. And you can use it in various applications. Okay, here is the diagrammatic visualization of Markov chains, and the sums of rows are equal to 1. And here is Markov Chain Monte Carlo, which is widely used. Markov Chain Monte Carlo method for the simulation of a distribution is any method producing an ergodic Markov chain whose stationary distribution is F. With like the previous definition, actually ergodic has no meaning. It's already ergodic. So it leads to stationary distribution. And as I said, the importance is that even if you don't have F, you can simulate from F using this method. So here's the algorithm that we can use from sampling from this distribution. And what we need assumptions, we need a finite state space, at least with the algorithm that I will give, and the probability on X. And it's the first Markov matrix, the initial Markov matrix that we can take. And it may be like random. And we need all like this if and only if condition. And at the beginning, J is unrelated to pi, and it will converge to pi. So here is the algorithm. And this A is known as the acceptance ratio. And it has pretty intuitive interpretation because like the acceptance ratio determines what you do with this like kernel. And you scale the kernel with, like with respect to this A. And also like if you won't change like if you won't change the state, then you just like scale with this quantity. And here's another example, but I'll skip it. So here are my references. And also thank you for your attention.